In the previous video, we saw how we can predict the direction a reaction will move to reach equilibrium. However, what would happen if we had a system at equilibrium and then we did something to disturb that equilibrium? Le Chatelier's principle tells us what the system will do. Chatelier's principle says that when a system at equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. There are three different ways that we'll discuss a disturbance to a system at equilibrium. The first one, and probably the easiest one to understand, is what happens when we change the reactant or product concentrations. The second disturbance we'll look at deals essentially with gas phase reactants or products, and that's what will happen if we change the pressure or volume of a system. The third disturbance, and the one that's really the most difficult to understand, is the disturbance of a change in temperature to a system at equilibrium. The first disturbance to an equilibrium system that we'll talk about is the change in concentration of either the reactants or products in a system that's at equilibrium. Let's look at the example of an equilibrium system where we have N2O4 gas in equilibrium with 2 moles of NO2 gas. Now, according to Le Chatelier's principle, what would happen if we added more N2O4 to the equilibrium system? We'd be adding a disturbance on this side. And so in order to minimize the disturbance, Le Chatelier's principle says that the amount of N2O4 must be reduced. So that means that the reaction would shift to the right to use up the N2O4 and to form more of the NO2. In general, we could say that if a reactant or product concentration is increased, the system will shift in the direction to remove the added compound. So, another example, if we added more nitrogen dioxide, the system would shift to remove the extra added nitrogen dioxide, so the reaction would shift to the left. Now, even though the system will be shifting in one direction or the other, it's important to remember that in this particular disturbance and change, the equilibrium constant for the system will remain constant. The equilibrium constant does not change when we change the concentration, and then the system reestablishes equilibrium. Another way you could think about Le Chatelier's principle when we're changing the concentration of reactants or products is you could imagine that we're essentially comparing Q after the change to the equilibrium constant. And so when you compare the reaction quotient and the equilibrium constant, that will also tell you which direction, right or left, the system will shift to reestablish equilibrium. Now, I know you're probably thinking, what would happen if, for example, some of the N2O4 concentration is decreased from this system by removing the N2O4 from the system? Well, I think I'll let you think about that a little bit longer and see if you could figure out an answer for that question. The second change or disturbance we'll look at is the effect of when we change a volume or pressure. And again, this will mainly take place when we have a reactant or product in the gas phase. Now, you should remember from your General Chemistry 1 class that an increase in volume will lead to a decrease in pressure. So essentially, we could talk about either the volume change or the pressure change, but overall, you should remember that volume and pressure are inversely related. When we think about this kind of change in Le Chatelier's principle, we'll think about it in terms of what the effect of the change in pressure will have on the system. Now let's consider the reaction where nitrogen gas reacts with hydrogen gas to form ammonia gas. Now, as we would expect with Le Chatelier's principle, if we have some disturbance in the system that increases the pressure of the system, then the system will try to regain equilibrium by shifting in the direction that reduces the pressure in the system. So again, the change will try to counteract or minimize the disturbance that has been created in the system. Now, as you'll recall, when you learned about the gas laws, we can reduce the pressure of a system by decreasing the moles of gas in the system. Now, this little bit of knowledge can help us understand which direction a reaction will shift, and it's not always going to be the case that reactions will always shift to the left or right with a decrease in pressure or an increase in pressure. Now, in this reaction, we have 4 total moles of gas on the reactant side, but we only have 2 moles of gas on the product side. So if we have a disturbance to this equilibrium system, by increasing the pressure, we can then decrease the pressure by shifting in the direction that will have the fewer moles of gas. So in this particular example, we can decrease the pressure in the system and reestablish equilibrium by shifting in the direction of the products, or shifting to the right. The final important note that we have to make regarding Le Chatelier's principle with changes in volume of pressure is that, just like changes in concentration, the equilibrium constant is going to remain the same anytime we make a change to the volume or pressure in a system at equilibrium. So once again, the equilibrium constant will remain the same even though we have a disturbance in the volume or the pressure of a system at equilibrium. The final disturbance to an equilibrium system that we'll talk about in terms of Le Chatelier's principle is what would happen if we changed the temperature of a system that was at equilibrium. Now, when we think about changes in temperature, it's important to realize that many chemical reactions have an increase or decrease in their heat or enthalpy. And so when we write a chemical equation at equilibrium, we also want to ask the question, is this system endothermic or exothermic? Let's look at the reaction between nitrogen and hydrogen gas to produce ammonia one more time. Now, this system, while it's at equilibrium, it's also an exothermic reaction. In other words, it gives off heat to the surroundings. Since it gives off heat to the surroundings, we could imagine that heat is actually a product in this reaction. If we add in that heat on the product side, then that can help us to understand what would happen when we change the temperature based on Le Chatelier's principle. Because essentially, if heat is a product, if we increase the temperature or we increase the heat, we're essentially increasing one of the products. And so to reduce the amount of that product, the reaction for this exothermic reaction would shift to the left to reduce that extra heat we added by increasing the temperature. Now, unlike the disturbances of changing the concentrations or changing the volume or pressure for a system at equilibrium, when we affect an equilibrium system by changing the temperature, there will be a change in the equilibrium constant. In the case of an exothermic reaction, since an increasing temperature causes the reaction to shift to the left, that means we're reducing the amount of product, we're increasing the amount of reactant, and so overall, when we increase the temperature of an exothermic reaction, we'll find that there's going to be a decrease in the value of the equilibrium constant. Now let's look at the same kind of disturbance, an increase in temperature, for a reaction that is endothermic, or that has a positive delta H. In this situation, since it's endothermic, we can imagine that heat is a reactant in the system. If heat is a reactant, then if we were to increase the temperature, we're essentially adding more reactant, and so for an endothermic reaction, the system will shift to the right to reduce the heat present in the system. Now, since the system is shifting to the right, that means we'll be increasing the concentration of the products, and we'll be decreasing the concentration of the reactants with this increase in temperature. Since the equilibrium constant is calculated by taking the products over the reactants, and the products are increasing in this situation, that means that for endothermic reactions, an increase in the temperature, which causes a shift to the right, will also lead to an increase in the value of the equilibrium constant. Now, it's important to remember that the only time the equilibrium constant will change is if there's a change in the temperature for a system at equilibrium. Changes in the concentration of reactants or products, or changes in the volume or pressure of a system at equilibrium will not change the equilibrium constant.